Hello and welcome again to my physics online video lecture series. In today's video I'm going to be talking about batteries and about what it is that batteries provide to a circuit, as well as how to sort of like analyze them within a simple circuit. So let's get into all that. Now recall that we have previously said that the circuit symbol for a battery might look like this, where I have a longer, thinner line and then kind of like a shorter, squatter line. But in actuality, a real battery consists not only of that, but also of some internal resistance. Okay, so this right here might be the full battery. And so maybe like you could, if you want to, mentally draw an outline of a simple like a double A or triple A battery here. Okay, there's some internal resistance to the battery. So battery has internal resistance. Now I can connect this battery to any number of other circuit elements. I could, for example, connect it to another battery, although that will be for another day's discussion. I can also connect it to a bunch of resistors that collectively form a load. So if I do that, then my connection might look something like this. So here's my internal resistance for the battery. I have a whole bunch of resistors that get connected together in some form or fashion. Those collectively get treated as a load resistance. The internal resistance, by the way, we usually represent with a lowercase r. Now, there's a few things that we might talk about with this battery. One is, what is it that the battery is actually supplying? If you pick up a double A or a triple A battery, you look on the side of it, let's say you've got yourself a double A battery, you look on the side, it says 1.5 volts. If you have a triple A battery and you look at the side of it, it says 1.5 volts. They do make other batteries. For example, if you get one of the batteries that in cross section looks like this, where there's the little terminal and the big terminal on the top, this one ends up being 9 volts. Okay, so let's say that you pick one of these batteries and it says 1.5 volts. You connect it to your load resistance. You take out a voltmeter, you put it across your load resistance like so, and you go and you measure how much voltage is there on this load resistance. What are you going to measure? Take a moment to think about it. Maybe pause the video, think about it, and then come back with your answer. So if you've paused your video and thought it over, I've told you that the battery is 1.5 volts. You may be tempted to say, therefore, there's 1.5 volts across this load resistor. That would not be the correct solution, however. Because I have this internal resistance, some of this voltage is going to be across the internal resistance and some of it's going to be across the load resistance. So this voltage that I've measured, V load, is also sometimes called terminal voltage, or delta V load. It's called terminal voltage. And it depends on not only the battery's 1.5 volts, but also on the relative values of the internal and load resistances. So what is this 1.5 volts in that case? Well, this is what's called the battery's EMF. We represent it with an epsilon. It looks kind of like a backwards 3, but it's an epsilon. This is called electromotive force. or EMF for short. And that is what this epsilon stands for. Essentially, this EMF is what you'd get if you didn't have a load resistance connected and you just took the voltmeter and connected it to the two terminals of the battery, assuming, of course, that the internal resistor, the voltmeter's internal resistance is very, very high. So if I take my battery right here, I'm going to orient it this way just for the heck of it. So here's my battery. This side is the plus terminal, so it gets the long thin line. This side's the minus terminal. It gets kind of the short fat rectangle part. And then I have some internal resistance in here. If I were to take a voltmeter and just measure like this without any load resistance attached, this one right here would be my EMF. So that's what your 1.5 volts are doing. But you now know that series and parallel connections exist between resistors. You know that now the internal resistance and the load resistance are in series with each other. And so that basically means that delta V load, the terminal voltage, plus delta V internal, essentially the one that's across the internal resistance, have to add up to the total epsilon that we have here. You also know that charges are conserved, and so that means that I have the same amount of current running through this internal resistor as I do through my load resistance. So again, we're referring to this diagram here. And if I have some current passing internally through the battery and through this load resistor, it's going to be the same amount of current. Same current goes through the load as goes through the internal resistance. What that means in turn is that my delta VL is equal to I times R load. And delta VR would be I times little r. And so this means that my EMF is I times big R, or big RL, or load resistance, plus little r, internal resistance. Okay, so that in turn allows me to figure out how much voltage drop I actually get across the load. It's going to be I times RL, but I itself, the current, must be epsilon divided by RL plus little r. Okay, that's just using series circuit analysis. And so if I want to figure out what the voltage drop across the load itself is, then delta V load is I times R load, which in turn looks like R load divided by R load plus little r, all times epsilon. Now, suppose that we take some limits here. So again, let's write that out. Delta V load, the terminal voltage, is the load resistance divided by the load resistance plus the internal resistance, all times epsilon. Now let's consider some limiting cases. Suppose that the load resistance is small. Maybe the internal resistance is like 10 ohms and my load resistance is only like 1 or 2 ohms. What happens if I make the load resistance bigger? Well, if I increase from a load resistance of 1 ohm to a load resistance of 2 ohms for a 10 ohm internal resistance, then my terminal voltage basically goes from a value of 1 over 1 plus 10, so 1/11 of epsilon, to 1 over 2 over 2 plus 10, 2/12, 1/6, roughly, though not quite, double what I had before. So for small values of the load, basically as you increase the load and resistance, the terminal voltage increases nearly, though not quite, linearly. If you make this sufficiently small compared to the internal resistance, then it will look pretty linear. Like if this is 1,000 and this is 1 or 2 or 3, it'll look pretty linear in that regime. So what happens though if we make RL really big? Like maybe the internal resistance is only 1 ohm or 10 ohms or something like that, and the load is 1,000,000 ohms. So I have 1,000,000 divided by 1,000,000 plus 1. That's practically 1. If I have 2,000,000 divided by 2,000,000 plus 1, that's still practically 1. So once this load resistance gets really large, so if the load resistance approaches infinity, or load resistance many, I'll do triple symbol for many times larger than R, the internal resistance, then terminal voltage, delta VL, will approach the value of the battery's EMF. So again, that's why this EMF is equivalent to the open terminal voltage, assuming that this has an internal resistance of, let's say like 10 mega ohms or something like that. It's some really big number, like infinity. Okay, 10 is not infinity, but this, we could say, approaches infinity. And we can get an approximation for what that means by using like 10 million ohms versus an internal resistance of 10 ohms or something. Okay, so that's basically how this thing behaves. Let's see a quick example of all this. And actually, I should note as well that delta V sub internal is just I times little r, and that ends up looking like epsilon times 1 minus RL over RL plus little r, for what it's worth. There's one other thing to note before doing the example, which is like power use. So you know that P is equal to I times epsilon. This is the total power from the battery. And besides the total power draw from the battery, there is the total sort of like useful power, or total power used by the load. And then there's also how much power is wasted on internal resistance, basically just heating the battery up. And so you could call this like the wasted power, if you'd like. So this one right here is essentially like how much work is actually being done by the battery on whatever device you're using. This one right here tells you how fast the battery will be drained. This is just waste. So let's get on to a quick example. All right, our brief example is to determine the terminal voltage for a 1.5 volt battery with internal resistance 2 ohms when it's connected to an 8 ohm load resistance. So delta V load is the terminal voltage. That's going to be the EMF times the load resistance divided by the sum of the load and internal resistances. That's 1.5 volts times 8 ohms divided by 8 plus 2 ohms. All right, 8 plus 2 is 10. That 1.5 over 10 is 0.15 times 8 is 1.2. So my terminal voltage here is 1.2. For what it's worth, the current is going to be 1.5 volts over 10 ohms, or 0.15 amps. It follows that the total power used, power is I times epsilon, would be 0.15 amps times 1.5 volts. This comes out to it comes out to 0.225 watts. The power that is actually being used, the useful power, is I times delta V load, and so that is 0.15 amps times 1.2 volts. That comes out to 0.18 watts. So we could call this the useful power. And then if you want to know the wasted power, it should be just the difference between these two, which is 0.45 watts. But we can also do that by doing I squared times a little r. So that is 0.15 amps squared times 2.0 ohms. So 0.15 squared is 0.225 times 2 is this is 0.0225. So that times 2 is 0.045. Left off a 0 when I said that before. So if you add these two together, you do in fact get this one. That's a good double check that you've done everything correctly. So this bottom one is like the wasted power. So let's call this wasted. And that is it for this little video. So hopefully you've learned what you need to from it, and thanks for watching.